Hello, Simple Rockets 2 fans. I recently made a submission to Croxy's Efficient Ascent and Orbit Vizzy contest, and in response I received a request to explain how my flight program works. So, here we go. As you can see, this is a relatively complicated program, but what it is doing is actually fairly simple. I set out to design the program around the idea of a real-life gravity turn, which I learned from the fountain of all knowledge, Wikipedia, is performed by making only a slight change in the rocket's pitch, and then letting gravity and angular momentum do the rest without a lot of additional steering. After the gravity turn is complete, and once the rocket's apoapsis is close to our target altitude, we have to make a burn to circularize our orbit. So let's jump into the code. The flight program has a couple of components that we'll be digging into. In the middle, we have the main program. Off to the left, we have a bunch of custom expressions, which are reusable groups of expressions that can be referenced throughout the flight program to compute a value based on some input. In computer programming, these are what we would call functions. Below the main program, we have a custom instruction that contains all the steps necessary to circularize our orbit. Custom instructions are similar to custom expressions, except that they can take actions instead of just computing a value, and they don't return a value. In computer programming, these would be called subroutines. In the top right is the evaluation program that computes our fuel consumption and score for the competition. I won't be going into that in this video. In the bottom right, we have a couple of event receivers that we will use to perform certain tasks in parallel with our main program. Let's start at the beginning with the main program. Here at the top of the program, we set a number of variables that dictate what pitch angle to set when initiating our gravity turn, what surface velocity to initiate the gravity turn at, and what thrust-to-weight ratio to use for the first stage of the launch. As soon as we activate the first stage, we broadcast a message to initiate our event receiver that will adjust the throttle to maintain a stable thrust-to-weight ratio. We then wait until we reach our target velocity and initiate our gravity turn. The method I'm using for the gravity turn could use some improvement. I'm setting a fixed pitch angle and then waiting for the direction of motion to come into alignment with that vector, at which point I unlock the heading and let the rocket gradually rotate as gravity, angular momentum, and atmospheric drag act on it. A better approach might be to set the pitch input to some value and wait for a certain angular velocity to be achieved before setting it back to zero. After the gravity turn is complete, I adjust the TWR and wait for fuel to run out. At this point, let's take a look at the stable TWR event receiver. Event receivers will execute whenever the specified message is broadcast and continue to execute in parallel with the main program and other event receivers until they have executed all of their instructions. Event receivers can also take a single input value. In this case, the input value is the thrust-to-weight ratio we want to maintain. However, in order to allow this to be changed while the receiver is running, we store it in a variable that our main program can update. We then loop while we have fuel and the abort variable has not been set to true, and every 500 milliseconds we set the throttle based on the ratio of our desired engine thrust to our maximum engine thrust. Since TWR is computed by dividing thrust by weight at sea level, we can compute the desired thrust by multiplying TWR by our current weight at sea level. Okay, back to our main program. Once stage 1 runs out of fuel, we jettison stage 1 and activate stage 2. At this point, we just go full throttle and lock our heading prograde. I'm not sure how different this would be from a real-life launch, nor if it is the most efficient, but it seemed like the simplest thing to do. Through experimentation, I found that in many cases, as a rocket's velocity and thrust-to-weight ratio increase at this phase of the launch, the time to apoapsis can begin to increase quite rapidly. And if this happens, it is easy to blow past our target apoapsis. To correct for this, I threw together a simple equation that reduces the throttle gradually as the time to apoapsis increases. When our apoapsis is within 400 meters of our target, we cut the throttle. If we reach our apoapsis without making our target altitude, we failed. If we made it, the next step is to make our orbit circular. And this is where things get complicated. I made this custom expression just to separate it from the main program. However, before we really drill into this code, we need to review a bunch of orbital mechanics and math. Presumably, everybody watching this video knows that to circularize your orbit, you want to burn at one of your apsides. In this case, the apoapsis. And from the apoapsis, you want to make a prograde burn until your altitude at periapsis is very close to the same as your altitude at apoapsis. There are two things we need to determine when making the necessary burn. First, the amount of delta V required, and by extension, the amount of time to burn for. And second, the orientation to maintain during the burn. In order to calculate delta V, we can use the concept of specific orbital energy. The specific orbital energy of a satellite is equal to the sum of its kinetic energy and its potential energy. As the satellite moves along its orbit, its specific orbital energy remains constant. But if it is an elliptical orbit, the amount of energy attributed to the potential and kinetic energy changes proportionally. What we're interested in is the difference in velocity between the apoapsis of our current elliptical orbit and the apoapsis of our target circular orbit. Since we would like the apoapsis to remain the same, potential energy at apoapsis is constant. Therefore, we can simply calculate the velocities based on the two different kinetic energies and take their difference. So let's break down the math. First, let's look at the equation for potential energy. -1 times mu over r, where mu is the product of the universal gravitational constant and the sum of the mass of our two bodies, in this case, Drew and our satellite. Since Drew is massive and our satellite is relatively tiny, we can ignore the mass of the satellite. And r is the distance from our satellite to the center of the planet. Now, let's look at the equation for specific orbital energy of an elliptical orbit. This is -1 times mu over 2 times our semi-major axis. Since our target orbit is circular, we can compute our target semi-major axis by adding the planet's mean sea level radius to our target altitude. We also need to find our current orbital energy. For this, we use the full equation for specific orbital energy, or our kinetic energy, v squared over 2, minus our potential energy, mu over r. In this case, I've dropped the -1 factor in our potential energy and simply subtract the value from our kinetic energy. Now that we know both our current and target orbital energies and the amount of potential energy to deduct from each, we can reverse the equation for kinetic energy to solve for V and take the difference. Delta V equals the square root of 2 times our target energy minus the potential energy at apoapsis minus the square root of 2 times our current energy minus the potential energy at apoapsis. Okay, Now that we know our planned delta V, we need to find out how long that will require us to burn for. Now, I could have simply used the fact that force equals mass times acceleration, and that change in velocity equals acceleration times time, and therefore computed burn time by dividing delta V by the maximum thrust divided by our craft's mass, but that would have been too easy. And it wouldn't have accounted for the changing mass of the rocket as we burn propellant. Thankfully, the trusty rocket equation comes to the rescue. The rocket equation states that delta V is equal to the effective exhaust velocity times the natural logarithm of the initial mass divided by the final mass. Using the fact that final mass is the initial mass minus the mass of the propellant used, we can substitute and solve for the mass of the propellant we need to burn. This is given by the equation initial mass times 1 minus 1 over e to the delta V divided by the exhaust velocity. Now that we know the amount of propellant, we can use the specific fuel consumption to find our burn time. Specific fuel consumption is simply the inverse of the exhaust velocity, and it has the units kilograms per Newton second. Therefore, we can find burn time by dividing the mass of the propellant by the specific fuel consumption times the thrust. And substituting the definition of specific fuel consumption, we get mass of the propellant times exhaust velocity divided by thrust. Now that we've covered all of the math for calculating delta V and burn time, you should be able to follow where those equations are used in initializing these variables. Potential at apoapsis, -1 times mu over r at apoapsis, which in this case is the planet's radius plus our altitude at apoapsis. Target orbit energy, -1 times mu over 2 times r at apoapsis. Delta V, the square root of 2 times target orbit energy minus potential at apoapsis, minus the square root of 2 times current orbit energy minus the potential energy at apoapsis. Exhaust velocity is calculated by multiplying acceleration due to gravity times specific impulse. Burn propellant mass, current mass times 1 minus 1 over e to the delta V over exhaust velocity. And lastly, burn time, burn propellant mass times exhaust velocity over thrust. Each of the purple symbols here is a reference to a custom expression. Some, like mu and specific orbital energy, don't take any input, they just compute a value. Others, like exp, take an input and use it to compute something. In this case, the input is the exponent to which the constant e is raised. Next, we need to determine the direction we want to be pointing when we make the burn. If a burn takes more than a fraction of a second, you'll want to maintain an angle of pitch that is parallel to the prograde vector at apoapsis. While setting the pitch to 0 or locking prograde and hoping for the best works in some cases, it yields poor results when burn times are longer. In order to find this direction, we need to review our classical orbital elements. So let's say that we have an orbit like this. What we want is to find a vector that represents the direction of our velocity at apoapsis. As most of you are probably well aware, we can describe an orbit based on its orbital elements. The first of which is the longitude of the ascending node, or in simple rockets 2, the right ascension. Assuming our orbit has a non-zero inclination, our orbit will pass through the celestial plane twice, at the ascending node, and at the descending node. The right ascension is the angle between the reference direction and our ascending node in the celestial plane. The next orbital element that we're interested in is the inclination, which is the degree of tilt between our orbital plane and the celestial plane. The last element that we will need is the argument of periapsis, which is the angle between the ascending node and the periapsis. If we know these three elements, we can find the direction of our velocity at apoapsis. But how do we do that? First, we start with a unit vector in the reference direction. In this case, we will use 0, 1, 0. We then rotate that vector around the up vector, 0, 0, 1, by our right ascension. We will call this vector v sub a for the ascending node. Next, we take the up vector and rotate it around v sub a by our inclination. We will call this v sub norm, since it is the normal for our orbital plane. Now, if we were to rotate v sub a around v sub norm by our argument of periapsis, we would have a vector pointing towards our periapsis. Rotate another 180 degrees, and we have our apoapsis. And rotate another 90 degrees, and we have the direction of our velocity at apoapsis, assuming a counterclockwise orbit. With that explained, the steps in the flight program to calculate the burn direction vector should be pretty clear. However, I'll touch briefly on all of these custom expressions for orbital elements. Unfortunately, Simple Rockets 2 only provides a few of the classical orbital elements. It provides inclination, eccentricity, and if the periaps is above the surface of the planet, then it is trivial to calculate the semi-major axis. However, it does not provide right ascension, argument of periapsis, or true anomaly. So let's take a quick look at how these are computed. It would take an entire video to go through all of these expressions one by one, but suffice it to say, they use the current position vector and the orbital velocity vector to compute all of the classical orbital elements. I'll provide a link to the source material for these equations in the description. One quirk is that the math I found was designed for a coordinate system where the z-axis is up and down. And I don't have a strong enough grasp on the math to switch it to the Simple Rockets 2 coordinate system where the y-axis is up and down, which is why I created these z-up based versions of the position and velocity vectors. In addition to the orbital parameter expressions, there are also expressions to perform vector rotations clockwise and counterclockwise, as well as calculating a vector rejection, which I'll explain in a moment. And up top, we have some basic gravitation-related information and some simple math functions. Getting back to our code, once we've computed the defining characteristics of our burn, we wait until we are 60% of our burn time plus 3 seconds from our apoapsis, and then we broadcast a message that initiates an event receiver that will maintain our desired orientation throughout the burn. The 3 seconds are to give the craft enough time to get into the correct orientation. Then, at 60% of our burn time to apoapsis, we start our burn. Rather than relying on our time estimates and burning for that entire duration, we continue the burn until we meet half of our success condition for reaching orbit, having an apoapsis and periapsis that sum to over 200 kilometers. In order to avoid overshooting our target and failing to achieve a circular orbit, we repeatedly recompute the remaining delta V and burn time, and when that drops below 2 seconds, we taper off the throttle. Lastly, let's take a look at the code that maintains orientation. In this event receiver, data is the PCI vector that represents the direction we want the craft to be pointing throughout the burn. In this particular example, we could probably just leave heading alone and set pitch based on the angle between our position vector and our desired direction vector. However, that would be incorrect if we were using this code for a significantly inclined orbit. As a satellite moves through its orbit, the heading of the prograde vector oscillates sinusoidally between east minus inclination at the ascending node to east plus inclination at the descending node. Therefore, we can calculate the heading by taking the cosine of the angle from the ascending node to our current position in orbit projected onto the celestial plane. The step of projecting the position onto the celestial plane is critical to accurately reflect the rate of change in heading for highly inclined orbits. For example, in a true polar orbit, the prograde heading snaps from due north to due south the instant it crosses the pole. The custom expression rejection takes two vectors and returns the component of the first that is perpendicular to the second, effectively projecting our position vector onto the celestial plane. So there you have it. There's a fair amount of math and programming concepts involved in this flight program, but hopefully it's a bit less of a mystery now. Thanks for watching. I'm Paul Wheeler. Keep calm and tinker on.